Hi, my name is Will Herman and this is my Engineering 305 video final exam. For this exam, each student is required to select 10 main topical areas in SAS and create an individual YouTube video to demonstrate understanding. We will be talking about three main subtopics, including the understanding of each concept, how to use SAS Jump to perform data analysis, hypothesis testing, forecasting, or prediction, depending on each of the topics, and how to analyze the results and the implications of the results to the business. The topics that I selected include ANOVA, chi-squared test, business demographics, hypothesis testing, mosaic interpretation, bivariate analysis, control charts, Pareto charts, reliability survival, and time series models. The first concept that I will go over is ANOVA. The ANOVA test is for variance between samples, variance inside of samples, and comparing three or more groups with one continuous response. Now some people might ask, why not do three pairwise t-tests to compare different samples? And the reason for that is the more tests you do, the greater your type 1 error will be. So if we can compile each of those tests into one test and just do one test, our type 1 error will be a lot smaller. And ANOVA does just that. We can use one test to compare the variability between three or more groups with one continuous response each. And as we can see below, we also have an F-test formula, which gives us our F value, or a value that is similar to a z-value, chi-squared value, but mainly, as we will see in the example, we will be focusing on the p-value to test for significance. Okay, so I will now go over to SAS Jump so we can look at an ANOVA example and how to use SAS to analyze the data. So for the ANOVA demonstration in SAS, I chose to use an example that we used in one of our previous PowerPoints that has to do with tensile strength as material undergoes 4 different heat treatments. And as we can see, we have our Y variable, or tensile strength, and we have all of our strengths listed. And then we categorize those strengths based on the different treatments that they undergo. And as we will see in our analysis, categorizing the tensile strengths into treatments in the second column will make for an easy analysis. And what we're really looking to do with ANOVA is see if we can reject the null hypothesis that the variability between each of the categories is the same. So once we have our data put into SAS, we can go ahead and go to Analyze, Fit Y by X. We will put our tensile strength in our Y slot, our treatment in our X slot, click OK. And we can see that we have our tensile strength values categorized into 4 different treatments. And we'll go ahead and click the red arrow and go to Means ANOVA. And here we can see that we can analyze the results. And we have a p-value down here as well as our f-value. But what we really care about is the p-value because it's going to tell us if we can reject the null hypothesis or not. And we will use a significance level of 0.05 because it's the most common or popular. And because our p-value is greater than our significance level, we cannot reject the null hypothesis that each of the treatment variabilities are the same. And basically in business, this is key because, for example, if we have 4 different machines producing the same part, we can test to see if the variability between the machines is different. And if it is, then we can go ahead and make adjustments accordingly. Perhaps a machine is creating more defective parts than another, and we can make the adjustments so that in the hopes that the machine will no longer produce more defectives than the others. So moving on, our second concept is the chi-squared test. And similar to the ANOVA test, we are trying to test to check to see if our null hypothesis can be rejected. And if our p-value is less than our significance level, again, we can reject the null hypothesis that our variables are independent of one another. And notice how I said independent of one another because the chi-squared test is all about testing to see if 2 categorical or nominal variables are independent of one another. And we should also note that counts are categorical, and as we will see in our example, we can see that counts are actually one of our variables. And as we can see below, the chi-squared formula gives us our chi-squared value. And similar to the f-value, again, we are not going to be looking at that very much, but we will be looking at the p-value because it'll tell us whether or not we can reject our null hypothesis or not. So here we have our chi-squared test example, and we are testing to see if gender and political party are independent of one another. And as I mentioned before, we have counts in our second column, and notice how our counts are in the form of D's and R's. Notice how there are 20 male Democrats and 30 male Republicans, and we are going to show how to conduct the chi-squared test and then analyze the results. So in order to conduct our chi-squared test, we will go ahead and go to Analyze, Fit Y by X. We will put gender in the Y slot, political party in the X slot. We will click OK. And notice how we are given a mosaic plot, but that will be discussed in a later portion of the video that talks specifically about mosaic plots. And notice how we have our Pearson value down here, which is our p-value, and it is less than our significance level because, again, we are using a significance level of 0.05. So therefore, we can reject the null hypothesis. And again, the null hypothesis states that the two variables are independent of one another. So therefore, we can accept our alternative hypothesis, which states that gender and political party depend on one another or are not independent. And a good business example for this specific test is, say, for example, you are campaigning as a Republican or a Democrat, and you would like to know whether or not gender and political party are independent of one another. And as you can see, they are dependent on one another. So maybe you can take whichever gender leans the other way or opposite of you, and maybe you can target them in your campaign and really try to get some more votes in that area. So our next concept is business demographics, and demographics are simply a statistical view of a population, generally including age, gender, income, schooling, occupation, and so on. And as you can see, they go hand in hand because using demographics and understanding them is critical for the success of your business. And we have some important traits that go with supporting businesses. And now at this point, we will move over to JUMP so we can see an example of a business demographics problem that JUMP gave us to analyze in their sample data section. So here we have our example for business demographics using JUMP, and I chose to use presidential elections, which is in the sample data library. And notice how this data contains the percent of votes cast for the Democratic nominee in U.S. elections, followed by the winners. And we can really do a few things with this data set. We can look at, for example, the distributions of percentages for votes casted for Democratic candidates throughout each of the years, whichever years we choose. And we can also, from a more demographic standpoint, look at something like a graph builder, state colored by winners for a given year. And so we can really do a lot in terms of business and demographics using JUMP. And this is just one of the examples that I chose to include in my video. So from a business implication standpoint, we can really show a lot using JUMP if we simply just put our data in and graph it using different types of charts and models. So at this time, I'll now go over the concept of hypothesis testing. And hypothesis testing is simply an act in statistics whereby an analyst tests an assumption regarding a population parameter. And we're testing significant, and we're trying to prove the alternative hypothesis, and which is the opposite of the null hypothesis. And we have a couple of different tests. We have the t-test, which is when you know the sample standard deviation, and we have the z-test when you know the population standard deviation. And we also have tests to see if the population mean is not equal to the hypothesized mean, which is two-tailed. We have the population mean is less than the hypothesized mean, which is one-tailed. And we have the population mean is greater than the hypothesized mean, which is also one-tailed. So again, significance is based off of the p-value. So moving on to the JUMP example, we can see on the right we have inside the diameter of a bearing in an aircraft landing gear system are known to have a standard deviation of 0.02 centimeters. A random sample of 15 bearings has an average inside diameter of 8.2535 centimeters. And we're going to test the hypothesis that the mean inside bearing of the sample is really not different than the overall population, 8.25 of bearings, using a two-sided test at alpha equals 0.05. So for time's sake, I've already put in the numbers into the hypothesis test on mean calculator in JUMP. And notice that because we know our population standard deviation, this is a z-test. and we were trying to prove the alternative hypothesis that the population mean is not equal to the hypothesized mean, which is a two-tailed test. And simply we just have to reveal the decision, and based on our p-value of 0.4979, which is a lot greater than our significance level of 0.05, we fail to reject the null hypothesis, and therefore we cannot prove our alternative hypothesis. So from a business implications standpoint, we can take samples of things such as diameters of bearings and test them against our population to see if they are not equal, less than, or greater than our population, and then maybe we can make adjustments to our machines based on our results. So at this time we will now go over our next concept of mosaic interpretation, and notice how we saw a mosaic plot earlier in the video when we did our chi-squared test, and now we will look at how to interpret it. So notice a mosaic plot is a graphical method for visualizing data from two or more qualitative variables, and it is often associated with chi-squared tests. So we're going to go ahead and go over to JUMP so we can look at an example of a mosaic plot and look at how to interpret it. So here we have the data set children's popularity, and notice how we can go over to the graph builder mosaic plot and run the script. So here we have our mosaic plot, and notice how we are comparing regions and goals, and we have three different goals. We have grades, popular, sports, and notice how for example for the suburban region we have 57.6% of students focusing on grades. We have for the rural region we have 38.3%, and we can kind of compare percentages across the different regions for this specific example and see how they compare to one another. So from a business implications standpoint, we can look at a mosaic plot like this and say, okay, we see that the focus on grades in the rural region is a lot lower than that for the suburban and urban regions, and therefore maybe the education department can put into practice some things that will help students focus more on their grades to increase things such as test scores and whatnot. So at this point we will now move on to our next concept of bivariate analysis, and it simply involves the analysis of two variables, often denoted as x and y, for the purpose of determining the empirical relationship between them. And when we do a bivariate analysis, we often look at the coefficient of determination, or r squared, and it's an indicator of how strong the correlation between two variables is. So 0%, for example, indicates that the model explains none of the variability of the response data around its mean, and 100% indicates quite the opposite. So an r-squared value of 0.20, for example, means that 20% of the dependent variable is predicted by the independent variable. So at this time we will now move over to JUMP so we can see an example of bivariate analysis in action. So here we have a data sheet in JUMP, and this is actually the data for our Engineering 305 project. And notice how we have all 30 MBA teams, and we have different data for each season. So we'll go ahead and go to Analyze Fit Y by X, and we will check to see if there is any correlation between the 2017-2018 win percentage and 2017-2018 3-point percentage. So we'll go ahead and put win percentage in the Y slot and 3-point percentage in the X slot. Click OK. And notice how we are given a bivariate fit, which is what we want, and we can go ahead and go fit line. And now that we fit the line, we are shown our r square value, and notice how our r square value is 0.2375, indicating 23% or 23.75% of the dependent variables predicted by the independent variable. So the model only explains 23.75% of the variability of the response data around its mean, which is not very good. We're looking for more of an r-squared value in the range of 75%. So therefore, we can see that there's no correlation or minimal correlation between 3-point percentage and win percentage in the 2017-2018 season in the NBA.